Okay, welcome back to the channel. We will be doing fluid mechanics. We will be dealing with hydrostatic today. We will be dealing with hydrostatic, the analysis of pressure, and we'll be also as well dealing with the hydrostatic force. First, let me introduce the chapter. When we talk about the hydrostatic, we are talking about if you see the word on its own, it's a hydro and a static. It means hydro means water, and static means a something that is at rest or at a stationary position. So I guess for this one we will understand that we're talking about like the stationary. You see here on we're talking about a stationary water or a stationary fluid. Can be oil, can be mercury, can be gas, but it's on a stationary position. First of all, we need to look at this thing, 5 principles of pressure that you must know on a hydrostatic, which the first I wrote here. It says that pressure of fluid is always acting perpendicular to the surface. What does this mean? These are the principles of a pressure on a fluid, right? When they say pressure of fluid is always acting perpendicular to the surface, they actually mean that if we have a surface where the fluid runs on a horizontal like this, the pressure will always act at a 90 degrees to it. And if we have maybe a surface that is staying on an incline like this, it means the pressure will always act perpendicular towards this surface. This is what this principle is saying. So we're always going to use this. Even on a curved surface, maybe we have a bank that is curved, our fluid pressure will always act at a 90 degrees, so it does not act on an angle. So this is the first principle. The second principle says that pressure always depends upon the height of liquid. I wrote something here saying meaning pressure always increases with depth. What I'm trying to say here is this: if we have a container like this filled with water, for an example, filled with water like this, and maybe the height of this water is 5 meter. This is the height of the water and to the surface, and I have another here which here I have water, but the height here it's 3. It simply means that the statement say pressure always depend upon the height of the fluid, meaning the pressure, the higher the height of the fluid, the more the pressure. The lesser the height, the lesser the pressure. So that's what here is going to happen, and I think we just have to take it to a special consideration. This is the most important principle to know. The principle number 3 says that pressure is the same in all directions following Pascal's law. We know that when we talk about Pascal's law, Pascal says that pressure will remain the same across all the circumferential surface, meaning if we have let me give an example about a cylinder like this, and suppose here we have an oil, right? And when the cylinder is like this, here it's a piston, here it's a piston like this, and it is like this. Maybe here it has a lever and it has a pedal here where we're going to press. When we press the pedal, we let the piston press the oil. Maybe we want to deliver something. What Pascal is saying according to this principle, he say that the pressure, like if you press this oil, one advantage of oil is that oil is non-compressible. This is one advantage of oil that we know. One advantage of fluid that we know, it's non-compressible. That's why it is used on a hydraulic on the hydraulic systems to lift heavy stuff is because it's non-compressible. So when we compress it like this, when we push it like this, the force will exert on the surface, and the force that is exerting on the surface will move across all this the circumference of the container, meaning the force here will be the same, will act towards all the position. That's what Pascals is saying. It this does not mean that if the force is pressing here, the pressure will only be felt on the left side. No, across all it will feel the pressure. That's what this law is saying. So it's a law of Pascals. And principle number 4 says that pressure of fluid is always proportional to density. Pressure of fluid is always proportional to density. Suppose we have two containers. Here it's oil. Let me make 3. Here it's water, and here it's mercury. We have oil, water, and mercury, right? We know the density of water, it's 100. The density of oil, it's oil here, is 850, and the density of water, it's 1000, and the density of mercury is 13,600. We know this. Then it means if these densities are different, the law says that pressure of fluid is always proportional to density. It means the pressure will increase or decrease according to the density of their fluid. If we have here, we calculate using the pressure here. We know the formula, it's pressure equals to rho g area, right? We can take it like this. If we subtract pressure here, we're gonna have 9.81, and here we're going to have the same area. It means we're gonna have a different density across all the 3 containers. It means even the pressure will be the same, will be different. So the higher the density, the higher the pressure we're going to get. So this is what this statement is saying. It means if you use oil and water, it won't make the same work because of the different intensity. So let us look at principle number 5. It says that pressure at each level height will always remain the same. What does this statement mean? This statement means that if we have pipes that it's like this pipe is going up. Let's say here it's a tank, right? This is a tank where all the pipes are taking water from, and this pipe is taking water here, and this one, it's coming here, it's going there, and here there's another one going up there. It says that pressure at each level height will always remain the same, meaning let's take 3 different heights. Height number 1 is this one. We say this height number 1, height number 2 is this one, this is height number 2, then this is a line number 3. Because of the bottom tank, the pressure here will always be the same. The pressure at this height, even at this height will be the same. The pressure at this height, at this height will remain the same. Doesn't matter the size of the pipes, but the pressure will always remain the same because they are on the same level. And you will see this when we are doing transmission of fluid. When we are doing a chapter of transmission of fluid, you will see that pressure, they are the same at the same height. Even here on number 3, they will be the same. The pressure will always remain the same. So that was an analysis of pressure on a hydrostatic. So we coming to look at different scenarios of a hydrostatic. First of all, I need to start with an open. I want to start with an open system where this is our water. First of all, we always going to regard the height of the water from the surface to the bottom. This is, we're going to name it our height. Number 2, we always going to look at the area, the length. It means we always going to look at what? Area. Number 3, we always going to look at the centroid. meaning the centroid is the center of this, where the pressure it's acting upon. And when it comes to the centroid, we always take the centroid. We can name this centroid here and say our centroid will be y bar, right? We always regard our centroid by taking the half of our height, meaning our centroid is equal to what? Height divided by 2, right? This is our centroid. So when we talk about a hydrostatic force, we're going to talk about hydrostatic force. I can name it HF, right? We always have to know that when the hydrostatic force is going to act just underneath the centroid, if our centroid line is here on the half, it means our hydrostatic must be on the bottom of it, somewhere here, meaning from the bottom to the hydrostatic point, this is where our hydrostatic going to be, hydrostatic force, meaning from the bottom to the line of hydrostatic, we're going to have one third of our height, and from here to the surface we're going to have 2/3 of our height. This is what it's going to happen, meaning we need to consider, I need us to consider the formula for hydrostatic force. I need us to consider the formula for hydrostatic force. Remember, Newton says that the pressure at the gravity is always is equals to the pressure at the normal force, meaning perpendicular equals to normal force. It's a Newton second law. It's telling us that this will remain in equilibrium. If there is a force applied here on the surface, will be the same with the force that is applying underneath. This force, we know automatically that is going to be the pressure and the area to get this force, and to get this one we know is going to be what? Mass and gravity. So we make a conclusion that PA equals to mass and gravity. But we need to break this out so that we can find values that are here. Let us break mass out. Where does mass come from? Mass comes from the weight of the water, meaning if we can find the density and the volume, we can get the mass, meaning density equals to mass divided by volume. We know this formula. Then let's make mass subject of the formula. Mass equals to density multiplied by volume. So we can come here and say pressure multiplied by area equals to density, gravity, and volume. So we now have what? This equation. From this equation, let us break volume. We know that volume is what? Volume equals to area multiplied by what? By length. This is what we know with what? With a volume. But on these instances, I need us to use our length as a height. I need us to use our length as a height. So we're going to have what? Pressure area equals to density G area and height, meaning we're gonna divide both sides with area. This will subtract this and this. Then we're going to have P, which is pressure, equals to density gravity, and area, no, not area, height. So this is our formula to get what? The pressure. And we're gonna use this formula to find what? A pressure. But when we are looking for the hydrostatic force, we're going to say hydrostatic force equals to density, gravity, area multiplied by y bar. It means we're coming back to the volume. This part here, it's a volume. So our y bar, we calculated it here, which is height divided by 2. So this is how you're going to get your pressure, and this is how you're going to get your what? You're going to get your hydrostatic force. So we can proceed and look at the scenario where we are given a triangle shape. If we are given a container that is in a triangle position like this, you must always take note that the height will be this side, right? And when you look at the center of centroid, the center of centroid will always going to be your height, you divide it by 2, and where your hydrostatic force is going to act will remain the same with this one. It's going to be 1/3 of h, 2/3 of h. This is where your hydrostatic force is going to act. upon. So but for your y bar, is going to be height divided by 2. So this one does not really change the scenario comparing to this one. All right, and you need to know that you're going to be given different types of shapes. You will be given different types of shapes, and you need to work them out. And you need to know as much you're given different types of shapes, their areas as well. Sometimes you'll be given a cube, sometimes you might be given a triangle, rectangle, sometimes you'll be given different kind. You just have to use your geometric skills to solve those things. And I need you to show you another formula where we're going to get that we found the horizontal pressure, and I want to show you another formula. So here, when they said determine the resultant force, we know we're going to use this HF. And when they say the position where it occurs, we have to find H. If they say find the position where it occurs, the formula will be like this. This is the position where our force will occur. Then we're going to have second moment of inertia, sine squared theta, and area multiplied by x bar. Let me use x bar plus x bar. Then in this formula, I just want to derive some stuff for you. Here H represent position where our hydrostatic force is going to act. Sometimes they will want you to find this, especially when you're going for the inclines and when you're going to do the curves, which we're gonna do them. So they will want you to find the position. So if we look at here, we have something here called IG. This is the second moment of inertia, or the second moment of area. So this second moment of inertia, it comes with different types of shapes. So in the same thing, you need to apply according to what shape you have. If you are given something like square or a triangle, you're gonna be given B and a D. So it means your x bar will be here. This is gonna be your x bar. 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 So it's gonna be here. So we know if we have an x bar, this is a strength 5, right? If you did strength 5, you will know what I'm talking about. So your IG for this shape is going to be what? B multiplied by D cubed divided by what? By 12. You see it? This is your IG for the shape like this one. If you are given a circular shape, like this one, it means your moment of inertia, it's going to be what? It's going to be pi 64 d to the power 4. This is you need to remember these formulas. I don't think they will give you on the formula sheet on fluid. You just have to know them. So usually they will give you these two scenarios and you have to apply this here. Then we come here. When we come here, we realize that we have what do we call it? We have an angle here. We have an angle here, which this angle, it will come from the position where your area it's seated. Maybe they gave you a gate and it's on an angle, so you're going to use that angle to substitute it there, and this is going to be your area of what you have. If it's the area of this, you have to find the area of this. If it's the area of a circle, you have to use the area of circle. And the x bars is the same with the y bar here. It's the same thing I showed you on a y bar. You're gonna use it to get the x bar. So this is what is happening with the formulas. And I need you to be aware of something. When it comes to these calculations, you always have to make sure you get the correct area. If you don't get the correct area, you're gonna have a problem when going forward, because if you get the area wrong, you're gonna get everything wrong. I prefer you do the areas and the moment of inertia separate, and you come to substitute them here rather than mixing all of them in one workout. That can still confuse your calculations, and I'm still trying to see what we can have here. All right. I want to step up the game, and I need us to look at the different shapes, which I want to start with a curve. I need to start with a curve. If we are given a scenario where we have a curve like this, right, and we are told that our fluid is running throughout here. This is our fluid. Let me name it H2O. It means this portion here, you see all this portion, it's our water, and we are told that this is our resultant, which I will say R. This is our force. It's our force where it's acting. I told you it's always gonna act what? Perpendicular to the surface. And they say that we must calculate this force. One thing we know, this force is not straight, it's with an angle now. It's sitting with an angle now. And as much it's seated with an angle, it means we have to find the components. When we come this side, we're gonna have what? A horizontal component. And we come this side, we're gonna have what? A vertical component. Meaning if we have this, we're gonna have a angle here, the angle that it's seated with. If this is the case, it means to find our R is going to be what? R squared equals to HC squared plus VC squared. Then you can say R equals to the root of HC plus VC squared. This is what is going to happen to find the force that is acting here, which is the resultant. And how are we going to find our horizontal component and our vertical component? Because we are working on this, it means our horizontal component will be this line. I need you to note something here. We first need to find the area of this portion where the water is submerged. If we have A here, we're gonna have A here, we're gonna have B here, we're gonna have C here. So we have the area ABC, right? You see it? So it means from here we're gonna have the height of water. At what height our water is situated. And here we're gonna have a distance from the surface top to where the area end. We're gonna have a X, and from A to B we're gonna have Y. This is what we're gonna have on our diagram. All right, let us look at how to get our horizontal component. To get a horizontal component, we need to have what? The density of water, if it's water, and we need to have a gravitational constant number. We need to have the area, and we need to have the bar, which it means we need to have what? An X bar, right? We need to have an X bar here. So this is the first formula to look onto. So what is the X bar? The X bar, I told you, it's gonna act upon here on a middle of the area. So this is here, this here is going to be our X bar. This is our X bar, and here is gonna be our Y bar, right? You see it? So this is our X bar. So it means we have to find the half of our height to get the X bar, remember? So in order to get this is height and 2. So the area will come from what? The area will come from the height. Where we get the area is gonna be area equals to what? Height multiplied by 1. Actually, it's height multiplied by length, and height is unknown for now, but length is going to be 1. This is what we know. Where do we get 1? If we take a close look here, we know that our surface, it has to go like this. It has to go like this, and the water must be filled over here. So we assume that we are going to measure our area with 1 meter. This is what we're going to use, unless stated otherwise. They can come and say that the length of the curved surface is 5. Then it means here on length you're gonna put 5. But if it's not mentioned, you always regard it as 1. Then that's it for that. And this is going to be the density 9,81. Then you're going to find your horizontal component. So let us look at the vertical component. Vertical component is going to be rho g and what? Area times length. It's going to be the same with this one here, where we know that P is what? P is the density of what is given. G is 9.81, and the area. Now the area on the vertical component is going to be different. The area is going to be the area of ABC. It's going to be the area of ABC, right? It means we need the area on the surface, which the area is going to be 2 over 3 xy. You see, if we are given a length here and we are given y here, it means this is going to be our area. 2/3 of what? Xy. This is going to be our area. Never forget this information. It's very, very important, and it's very, very crucial. I need to add, if we are given an area of a full circle, let's say, you see, this is not a full circle, it is just a shape that I cannot explain what it is. So it's just a shape like this. So you're gonna use this kind of an area. Usually you'll be given x and y, but sometimes they might give you a full circle. For an example, they give you a full circle like this. They tell you that this water is submerged on a full circle, but they don't really gonna draw the full circle. They're just gonna draw the semi of it. If it's a full circle, your area is going to be pi times radius squared. Usually I know they will give you a radius. They're just gonna make a radius, and this is what you're gonna do for a full circle. This is how you're gonna find your area. Or if they give you diameter, it can be pi over 4 d squared. It's still one and the same thing. And if you are given a segment, sometimes they will mention on a statement that a segment is given, then you know you have to use the area of segment, which the area of segment is theta 2 multiplied by r squared. But on a segment, I need you to note something. On this theta, it must be calculated in radians. That's what we know about segment. It must be calculated in radians. If suppose you are given an angle of 80, how to convert 80 degrees to radians? You have to multiply it with pi over 180. If you multiply 80 with pi over 180, it's gonna give you a radiant number. It's gonna give you a radiant number. And we will be able to find our vertical component. Then we're gonna use whatever the angle we get, and we're gonna substitute it here, and we're gonna find our length. And let us look at, if we have horizontal component and vertical component. I want to take this picture here. Look at this picture. I'm taking this. This is our R, remember? It's our R. And I want to take this here. It's our horizontal component. And I want to take this here. It's our vertical component. You see them, right? Then, if that is the case, here is our theta. How are we going to get our theta? it means you can complete a quadrant, meaning you complete here, you just draw constructed lines here, meaning we know automatically that if this is a beautiful constructed square, this theta will be the same as this one here. And if here we found 5 and here we found 4, and it means 5 will be the same with what? With the 5 here, and 4 will be the same with the 4 here. So you can work both from this triangle or this triangle to find your theta. Let us use the SOHCAHTOA rule and see which sign are we going to need. SOHCAHTOA. Right, from here I'm gonna have 90 degrees here. We always say that adjacent is the one between the angle and the 90 degrees. So here's my adjacent, here's my hypotenuse, here's my opposite. So what do I want? I want my angle. And what side do I have? I have sides of adjacent and I have side of what? Hypotenuse. Even if you have the resultant here, you can still use the resultant to get your angle. I'm just want to show you just for the sake of showing you, so that you must not forget about this. So me, I'm going to use adjacent and opposite. Then it means my adjacent and opposite is here on tan. Then I'm going to say tan theta equals to opposite over adjacent. Then which my theta equals to tan inverse of opposite, it's 4 over 5. Then I'm gonna get, let me pick my calculator there. I'm gonna have tan inverse of 4 over 5. I'm gonna have an angle of 38.66. So this is my angle here, 38.66. Right, you got it. So it is like that, and we are done with a curve. So the curve is not really stressing a lot if you know these things. Mind you, on a curve, sometimes they can bring a curve that looks like this. Let me show you here. They can bring a curve that looks like this. And they say it from here, but they make a line like this, and they say the surface of the water is here, and this is water going there, and they just say here it's our H2O. If you take a close look from here to here, it's not a curve. The curve starts from here to here. So it means they gave you combination of what? Maybe they're gonna give you a rectangle here, and they will tell you that this is 4, and the curve it's at a radius of 5. I'm giving you an example. So they give you combination of a curve and what? And a rectangle. So when you come to your areas, you always make the two areas separate and you add them together and you substitute them here, because you need to take an area to the surface, not to the end of the bank. You need to take it from the surface. So this is what you must also expect. Let me look at one example and I show you. I think I've seen something like that. Yes, here it is. Take a look on this. You see here, they give you a curve here. They give you a radius of 4. From here to this radius is a radius of 4. So it means you have two areas, area 1 and area 2. Do you see it? Look what they did. They say a dam wall has a base in the shape of a quadrant of a circle. They told you it's a circle. So, and already you know an area of a circle, full circle. So they said with 4 meter radius. So they gave you radius above the quadrant, and the wall has a vertical face. You see, this is a vertical face of 3 meter. Calculate the resultant thrust on the wall if the dam is full of water. So they need a resultant. First of all, you need to calculate your horizontal component and your vertical component and put them on your R. So here they started with the X. It means it's a vertical component. They use this and this and a 7. Where did they get the 7? It means the 7 it's it's 4 plus 3. They actually, this is according to how I showed you, this is a HV. Remember the formula here, it's HV, where you're gonna say x bar and you say 7 divided by 2. You see the 2 here is the one they got from there, and this is what they just did, and they found the area. Look, I just want to concentrate here. The main thing actually I want to talk about with you is this. If you look closely here, they said area ABC, area ABC. It means it includes the triangle and this one of 4. You see it? They say pi over 4 times 4 squared. 4 is the radius, you see? So this is for the one, this is for circle, plus 4 times 3 is for the rectangle. You see, they brought them together and they substitute that amount here to get the vertical component, and they do that and they got the correct answer. So this is what you will be doing along. And on the next example, they gave you, they say a dam hole is shaped as 1/6 of a circle. Calculate the resultant thrust on the radius. If you see here the drawing, they give you an angle. You see, automatically when you are given an angle, you must know this is a segment. Okay, it's a segment. So they give you a radius of 5 with a 60. So it means when you come to the solution, you see they used that formula for the segment. It's here. I gave it to you, segment. You see it? It's here. So they use it to get what? The meter. And after they get the area of the segment, they substitute it here, and they get it. They substitute it here. They minus that area with the one they want on the outside, because there's an area on the outside, and they found the correct thing. So I was just want to show you the relationships of the area and different types of drawings. If you come here as well, you see they have a curve, and here they have what? A rectangle thing. So always regard these things, always check over them. Don't just avoid such information. It's important. So let us go there and apply the correct things. Okay, and I've covered a lot this far, and I just want to talk about the last thing, which it's a gate. Sometimes they like to ask a question of a gate. They like to ask a question of a gate, where they will say, let me give a close example. Let me give a close example over here, where they ask a gate. Usually a gate, they love to bring it in an incline. Usually I want to talk about an incline. We know that incline is in earth mechanics, we're speaking about maybe this is a load, where we say either it's going up. If it's going up, this is a force applied. There will be force of friction, force of gravity parallel, force of gravity, normal force. We remember all these things. So I just want to bring you an idea of the inclined planes. This is what it's all about. So even here, we're still going to use such information that we remember from here to answer questions. But let me first start with a simple one here. Suppose you are given a wall here. This is a wall, and on this wall they've put a hinge here, and after they put a hinge, they install a gate, a big gate here, and they say this gate is 5 meters, and the thickness of the gate, maybe they say it's 3. Do you see it? And from here it has a closure here. This gate has a closure here. Then this is a wall as well. This is a wall. So from here there's a plenty of fluid. Maybe they close it here. Even this wall, there's a plenty of water. Maybe we want to retain water. We want to retain water not to come out. So whenever we need it, it's more like a valve, in fact. So whenever we push the hinge this side, we go in, the water will pass out. So we say that here we're going to have a pressure which is P. So we need a certain pressure to open the gate the gate so that the water can pass out. So why am I drawing this? I want to draw you that to tell you that whenever you are given a scenario about the gate, always make a simple geometric drawing. Simple geometric drawing. You just say, oh, all right, this is my height of a gate. You just draw one line like this. My gate, it means it must go with a theta here. Then you draw a line going there with a theta. You see? Then from here to here I will need a height. It means here you're gonna have a small height like this one here, and the other height you will be given. I'm gonna look at one example here with you, and I'll be explaining. And you see already you have in a triangle, so whatever that you will need here, you must work it from the triangle, which I know you can do the triangle problems. Let's look at one example from this wonderful book. Let us look here. They say a gate is showing in 3 meter wide. It means the width of a gate. This is the area of gate. Area of gate. This is the area of gate. They say it's 3 meter wide. It's 3 meter wide. And when we look at the drawing, they say from here to here it's 5. So it's 5. So you can now find the area of a gate. It means it's what? Length times wide. Right? You see it? Then you can get it. 5 times 3, then you can get the length of the gate. And you come here, they say calculate the resultant force on the gate due to its fresh water, the height at which the resultant force occurs from the free surface, the force P exerted by the wall, the reaction on the hinge. They want all that things. This is kind of a question, are the questions that comes at the exam. So prepare yourself for the examples like this one. So if we check, they say from the bottom from the wall bottom to the surface of water is 12 meter. So we automatically have the height of what? Our water. We come to the gate. Our gate is 5 and it's 3, and they say the position where it stays, it's 4. So automatically we can make a small triangle like I just shown you. You see here they've made it a small triangle, they make 4, and here they break this into 2, right? You see it. Then they say 2.5, 2.5, it's 5. Why are they doing this? They are doing this so that they can find a center of centroid. They can find a center of centroid. So this is what is going to happen. First, they say the resultant force. It means we need what? A force. To find a force, we have to get P, G, area, and X bar, right? But we have a triangle. How to find a X bar of a triangle? How to find the X bar of triangle? Here is the X bar. We know if it was this, we're going to take height, we divided by 2. But on this one, what is going to happen? Suppose here, look at here. They are telling you the X bar will always act from the half. If you see from this line to this line, there will be a half. X bar will always act on the half from this line. Meaning, if we have 2.5 this side, and we know that we have an angle here. You see, you have an angle which is 36.87 here. The angle that is here is the same as the angle that is here. Do you agree with me? Because of the 90 degrees here, this angle will be the same with this one. So we know we can make a small triangle. A small triangle, it's going to be like this. Sorry to make it big and ugly. So this is going to be our 36.87. Is this, let me name it triangle 1. Is this triangle 1? Ne? Then we know from this side is 2.5. So if you have one side, and here's 90 degrees, even here it's 90 degrees. If you have one side which is 2.5, right, and you need this side of X, which is your center of centroid, you can use opposite and hypotenuse, which is sine. You can use sine 36.87 equals to sine 36.87 equals to opposite is X over 2.5. Then let's see how much you're gonna get. 2.5 multiplied by sine 36.87, which is 1.5. It means this position from this X from here to here, it's what? It's 1.5. It means even here from here it's gonna be what? 1.5. This is how we got our centroid. One can come and say that if you have a height of 3 meters, you can just divide it by 2 and get the centroid, which is still okay. So there's a many way to kill a cat, and at the end of the day the cat must die, because you see here they used their method, I used my method. You can still use the other method to find your centroid, but that does not determine that this 1.5 is not a centroid. It was just to find the half of this length, right? The real centroid will come from subtracting the total amount, because it's from the bottom. Can you see? This is from bottom to top, so we need at least here, we need this here. The centroid actually will act from here going up, so we need to subtract out this value, which is going to be what? 1.5. So we're going to say 12 minus 1.5 is going to give us this x bar. You see, then we're going to come here and say we know it's water, it's 1009.8. the area of a gate, remember they need but they say force on a gate, so area of a gate multiplied by the centroid, then it's going to give us what is needed. Then the height, when they say height, they actually looking for this. When they say height, remember I showed you here, when they say height they actually looking for this. So let's come back. They say height, so the height, it's gonna be this one over here. So this is our height. So this is our height here. I, remember I, it's second moment of inertia, because our gate is a rectangle, we're gonna use this BD, right? Then you must be very careful when you substitute your B and a D, because it's a 3 and 5. You don't just take any. I've shown you that you don't just take any. You have to know that the B is the one on top and the D is the one like a height. You see here, if it's like this is your D, you see, and this is your this is your B, and this is your D. This is your B and this is your D. This is how it's supposed to be. So you don't just take any. If you take any, you're gonna make mistake. You're gonna make a huge mistake. So let us continue. It's gonna be B and a D. Then here it's a sine. On a sine, remember already you have found the angle, which is 36.87. Guys, please don't confuse this angle with the one for segment, where the segment is 2 plus that one on the segment on a curve. No, please don't confuse that with this. It's not the same thing, right? So here is the angle you got from the gate, is the angle of the gate. Then you put it all together here, then you put your centroid, then you're gonna get your height. So now they need a pressure on P. Getting the pressure on P, it's gonna be you're gonna use your moment. You're gonna use your moment. You're gonna draw a beam where you're gonna have if you draw a beam like this one, and you know this is your P, and we know that from P to that one we're going to have 3. From P to this we're gonna have a height of 3. Then from that P here is on the middle where your force act. Remember, this is the force we found on H. Remember, on H 10.57, our force is 1545. We're gonna use that force here. Which they used here. You see, then after they use the force, they take moments P times 3, 2.381, which comes from the half of this. Then they take this distance here, which is x. You see it? So then they were able to get the pressure. So where do they get this? They get it from the centroid. It means it's at the point of centroid. The centroid, the position where our F is going to act. Let me show you something before I forgot. Let me show you something. Look, that thing, it's like this, right? It's like this, it's P, right? And we spoke that this is going to be 2.5 it's the half. Then this is going to give us what? A centroid, and it was 12. This is going to give us a centroid, which is x. We got it as 10.5, right? I don't remember. Then this is where our hinge is. We found force, which force is 1545, right? And we found height, which height is 10.48. I want you to note something. You have to measure from top going down here. You measure, you can start here, you measure it, you measure it, you measure it, then you're gonna get your 10.5. Where your 10.5 acts, that's where your force acts. With this force, not on the centroid. Not on the centroid. I always tell people that force always act underneath the centroid. Then it's gonna be your what? 10.5 what? Then it's gonna be here. Then it means you have to find a new value here, because from here to here is 2.5, but from here to here is not 2.5. Then you have to make another calculations to get this length. So this length is gonna help you on your beam. When you have a beam like this, you know this is your P, and you have 3, and you have F. F is this force, but this force does not act on the distance of 2.5. It acts on the distance of x. So you have to find x, then you're gonna get your P. So thank you very much. We are done with hydrostatic. Just go try solve as many questions as you can. Thank you.